So welcome all of you to the lecture of Power System Dynamics and Control course. So today we'll continue the representation of synchronous machines. In the last class, what we have discussed, the representation regarding representation of machines, that how we can, in fact, with a constant impedance load, how we can form the reduced Y-bus matrix, and then we can find the also we can uh, transform the DQ parameters to the common frame of reference. All these things we have discussed, and also we finally got the reduced Y-bus matrix where the size of the Y-bus was ng by ng, right? Already we have seen this. This is what we derived in the last class. Okay, so this will be your complete equation where you can see this equation we got, right? Ig0 yin transpose y bus dash, and this is the extended y bus where the size of the y bus matrix is ng plus 1 ng plus n into ng plus n, right? And this Vn is your, it represents your bus voltages, and E double dash represents your internal voltage of the generator. And after manipulating, we get Vn in terms of internal EMF of the generators, and then by substituting Vn into the second equation, we found the Ig, equation of Ig, right? Substituting in the first equation, right? From the second equation, we found Vn. Then in the substituting in the second equation, we found Ig in terms of internal EMF, right? Ig is the current injected by the generator. And now you know Ig, the size of Ig is Ng by 1, and E dash is the internal EMF of generator, that size is also Ng by 1. So therefore, this reduced Y-bus matrix has a size of Ng by Ng, right? Okay, so already we have seen this, and here we can very clearly say that your injected current from generator is represented in terms of the internal EMF, right? So now we'll talk about the initial conditions. Why it is important, initial conditions? Because whenever we'll start solving any differential equation, we need the initial condition. In fact, it is taught or to you or not, I don't know, but we'll see it in the transient stability analysis and even also small signal stability analysis. We need to know the initial condition. We need to initialize the parameters. Then we can solve and we can reach the final solution. We can get the final solution of the these equations, whatever we have derived, this DAE, differential algebraic equation, right? So now the question is how to initialize all these parameters. So let us see how we can do it, right? So therefore, before doing any stability analysis, the system along with its generators, loads and network should be initialized. It is very important, right? So these are the steps which should be followed for initializing the system. So these are the following are the steps. So the first step is in the step 1, what we do, the network real and reactive power balance equation should be solved. So by solving, what we'll get by solving these equations, we know the real and reactive power balance equation. By solving those equations, we'll get the bus voltage, information about bus voltage. That means we'll get the values of the bus voltage magnitude and the angle with respect to the reference bus. Okay. So then how we can solve this? If we have a small network, 2-bus network, we can directly solve it. But if we have a huge network, then we need to solve it using the load flow analysis, right? So therefore we require load flow analysis, which is in fact very essential. Load flow analysis is generally used for steady state analysis, but here we require load flow analysis just to initialize the parameters. Okay, so therefore that is what solving this. It mentions solving these real and reactive power balance equations. It is nothing but doing the load flow analysis, right? Those who have done load flow studies, they must be knowing that the important equation in the load flow analysis is the power balance equation, right? This Pi equal to Pgi minus Pdi, right? Equal to summation of Yij Vi Vj, right? And e to the power j of whatever theta I minus theta j minus alpha, whatever it is, sir. It is actually e to the power j of, already we have mentioned this, right? Alpha I j minus theta I minus theta j. Okay, so plus theta I. So already, so solving this equation Pi and Qi is nothing but it is solving the load flow analysis, right? Doing the load flow analysis. So after the load flow analysis, what we get from the load flow analysis? In fact, from the load flow analysis, we get the information of voltage and voltage angle, right? Voltage magnitude and voltage angle at a particular bus. Okay. Then then we find the complex voltage. Complex voltage is nothing but Vi theta I. Then real and reactive power injections also we get at a particular bus, right? Okay, then step 2. So in step 2, what do we do? We'll find the internal load angle of each generator. Okay, so how we'll find this? We know the equation of internal EMF. The equation for internal EMF already we derived in the common reference frame, that is equal to EI to the power j delta I. It is for ith generator, right? Equal to Vi e to the power j theta I plus Rsi plus xqi into Igi e to the power j phi gi. Phi gi is the angle between the voltage and the current, right? Okay. So, so from this equation, we can calculate this voltage because we know Vi from the load flow analysis, right? Theta I also we know. All these parameters we know, parameters of the generator. And Igi also we can find out because Ii we know. Ii is known to us from the load flow analysis. We know Ii is nothing but Igi minus Idi, right? So therefore your Igi we can find, that is Ii plus Idi, right? So that is, idea is the load, demand current or load current, you can say, right? Okay. So after load flow analysis, the network bus voltages are known. The currents generated by each generator are also known. With this information, an internal voltage can be defined. So this internal voltage we can now calculate from this equation, from where we can find the internal load angle, or we can say rotor angle, right? Then coming to the step 3, in the step 3, then we calculate the dq axis components of voltages and currents and fluxes. So we know this angle because this rotor angle and network bus voltage angles are essential in order to find the dq axis component, right? So as soon as we know the initial values of these parameters, then we can easily find the DQ axis components of voltages and currents, right? So this is how we can calculate the DQ axis component voltages and currents. So VDI we know is nothing but VI sine delta I minus theta I. So we know delta I and VI and theta I. Just substituting the values, we'll find VDI. Similarly, we'll find VQI also because we know VI delta I theta I, right? Similarly, all these equations we can evaluate one by one, right? Also, we can find IDI, initial value of IDI, IQI, right? EDI dash, EQI dash, right? EFDI. Just we need to substitute one by one. So it's like if we'll write a program, we have to write all these equations sequentially in order to initialize all these parameters. First, we need to solve the load flow. These are the steps, right? So first step is we need to solve the load flow. Then from the load flow, whatever information we get, then we calculate the internal load angle or the rotor angle of the generator, each of the generator. Then by substituting those values, whatever we get from the load flow and the internal load angle of the generators, we'll get all these values sequentially. As mentioned here, so we'll get sequentially all the values. Then we'll calculate psi1 di, psi2 qi, right? Then we'll find RFI, VRI, Vreference I, then omega I, right? All these values we can find. PSVI, then PCHI, TMI, TI, everything we'll find, right? So now our initialization process is complete. So once the initialization is over, then we'll go for the stability analysis, right? So in order to do the stability analysis, we have the differential algebraic equation, right? DAE, we call it DAE of the system. That is the differential algebraic equation for the whole system. So we know the DAI, this is like this, right? This is your differential algebraic equation of your system, including generator modeling, turbine modeling, exciter modeling, then the rotor swing equation, right? Everything is included in these equations. And through these equations, we can analyze the stability of the system based on our requirement. If we are doing small signal stability analysis, we need to linearize the system and do the analysis. If we are doing transient stability analysis, we have to directly apply the integration method, integration techniques, right? To solve these equations to find the time domain response. Okay. So this is how we approach, right? So here I means 1 to NG, where NG is the generators are connected to the network, right? For all the generators, this is valid, right? Then obviously the network equations are there, which are useful for load flow analysis, right? Okay. So now the synchronous machine model, along with the exciter, turbine, and speed governor model is given here, which can be simplified significantly by making some assumptions, right? So this will be by, okay, not by making some assumptions. Okay, actually, whatever till now we have seen the modeling, it is exact model of the system. So now if we take some assumption, then the model will be simplified, and the simplified model also gives the results, though it is not accurate, but it gives proper information about the system. Like already you have studied the classical stability analysis, right? In the classical stability analysis, whatever model we consider, that is the most simplest model. And through that model, even if it is not giving the accurate result, but still it gives information about the stability of the system, right? So that means we can assess the stability of the system from the simplest model of the system. So similarly, that the classical model is the most simplest model. And if a little bit go above and go above, then there are many different types of models. So we'll read all these models, we'll study all these models here in this class one by one. Okay. So this simplification can lead to significant reduction in computational complexity. So computational complexity is reduces because these representations of different models in fact gives it is applicable for different application. Like only if you know the information about the stability assessment, then we can just go for classical model, and classical model is sufficient. It will give the information. But if you know deeply about the system parameters, the states, right? Different states in the system, then we need to go for the exact model. That is essential, right? So the various models that can be derived by simplifying these equations will be discussed now. Now let us see. This is the first model. It is called subtransient model with starter and network transients neglected. Okay, subtransient model means whatever we are studying till now, all the equations will be considered, but only we are neglecting here the network transients. So whatever network equation, whatever algebraic equation we have derived till now for the network, that is power balance equation or whatever, those equations are not really the transient equation of the network. Okay, so if we'll consider the transient of the network, because the transient of the network is faster, very fast as compared to the uh, rotor transient of that generator, synchronous generator. As the starter of the synchronous generator is connected to the network, we can consider the starter transient along with the network transient, but it is much more faster than the rotor transient. If we'll compare, right, it is very fast. So therefore, the net generally in this analogy, in order to comply or in order to make it comply with the rotor transient, we neglect the network transients along with the starter transient, because starter is connected with the network, right? So therefore, here the subtransient model represents with the neglecting the starter and network transients. Okay, so the starter, which is connected to the rest of the network electrically, has very fast transients as compared to the rotor. So compared to the slow dynamics of the rotor, the starter dynamics can be considered to be very fast, and hence any change or disturbance in the starter or the network can be considered as an instantaneous change without any dynamics. Okay, so this leads to reduction in computational complexity drastically, as the network transient also need not be considered along with the starter transients. With these assumptions, what we can conclude that the synchronous machine dynamics along with exciter, turbine and governor can be given as this. So starter transient we neglected, therefore all the derivative terms of starter parameters like psi d dot and psi q dot, they are considered 0. So here the simple equation we'll get for psi d and psi q, and then we'll get obviously the differential equation of the starter side with the time constant t associated with TDO dash and then TDO double dash. All these equations will remain. And along with that, we'll have the swing equation that represents the rotor dynamics. and obviously the uh, exciter equations, then your turbine equations, and along with that the stator algebraic equations, right? Okay, so now we have this is the complete set of equation which we represent for the subtransient model, right? Which represents the subtransient model. Now substituting psi d and psi q in these two equations, what we'll get? We'll get just substituting these values. Instead of psi d we substitute vq plus rsiq. Instead of psi q we substituted minus vd minus rsid, right? So now by multiplying the equation, first equation by J1 and adding both the equations, what will happen? What we'll get? We'll get this equation, right? So we'll get Vd plus Rsid plus JVq plus Rsiq. That will be equal to this. That is the left hand side of both the equations added with the multiplication of J1, right? Now little manipulation we will do just by considering xd double dash, jxd double dash. We will bring jxd double dash this part to the right hand side and we'll add jxd double dash here and also subtract jxd double dash. Just little manipulation, by doing little manipulation we'll get this equation, right? So this will be your equation where we can see here this will just manipulating the real and imaginary part, will get Vd plus jVq plus Rs plus jxd double dash Id plus jiq, right? So here we are adding a term that is known as minus of xd double dash iq, right? Both the side, both left hand side and right hand side. So therefore in the left hand side we'll get this term, extra term, right? So previously it was xq dash iq and now it is added in the left hand side also and right hand side, both sides. So therefore it will be xq dash double dash minus xd double dash into iq, right? This is the only extra term we get and this term is taken to the right hand side. Now just manipulating we'll get Vd plus jVq Rs plus jxd double dash Id plus jiq. Now what this equation indicates, this is your terminal voltage of the generator, right? Terminal voltage of the generator represented in the dq axis parameters. Similarly, this is your current injected by the generator at the terminal in the dq axis parameter, id plus jiq, right? And this is your parameter inside the generator, right? So now if I will multiply this in order to convert this equation into common reference frame, I have to multiply with e to the power j of delta minus pi by 2, right? So that will give me. So before that, let us assume the left hand side is the internal EMF. So that is E double dash. Okay. So this is the subtransient voltage E double dash, that is equal to Vd plus. So E double dash will have two components. One is your, that is Ed double dash plus Jeq double dash. So that will be equal to this. So now this in the DQ reference frame of that particular generator, we are saying that your internal EMF is equal to the terminal voltage plus current, terminal current into the Rs plus Jxt double dash, right? Now if we'll represent this equation now in terms of equivalent form, so this equation can be further simplified by assuming the effect of saliency during subtransient. So effect of saliency if we'll neglect, then your xq double dash will be equal to xd double dash. Okay. For cylindrical rotor case, this is equal, and if we'll in the salient pole machine also, if we'll neglect the saliency effect, then we can assume that xq double dash is equal to xd dash double dash. So therefore this term will also become 0. So therefore by again assuming that the effect of saliency in subtangent model is negligible, then we can write like this. The equation is e double dash equal to ed double dash plus jeq double dash equal to this, right? And ed double dash is nothing but this is now in a simplified form, right? So we have neglected this one, this part is becoming 0, right? So then your ed double dash will become this and eq double dash will become this, right? Okay. So now if we'll represent the equivalent circuit model of this subtangent model, equivalent circuit of the subtangent model, then we have to convert this equation into RI axis, that is common reference frame. So representing this equation in the common reference frame, we'll get ED double dash plus EQ double dash multiplied with e to the power j delta minus pi by 2, because e to the power j delta minus pi by 2 will be multiplied in the whole equation. So we need to convert into the common reference frame. So now this will be your equivalent circuit, right? So you can see here the equivalent circuit will look like this. This is your terminal voltage, generator terminal voltage, that is VD plus JVQ, which is multiplied with, because it is represented in the common reference frame in the RI axis. So therefore it is e to the power j delta minus pi by 2. And similarly the current, and these are the parameters, and this is your internal EMF, ED double dash plus JEQ double dash e to the power j of delta minus pi by 2, right? Okay, so now your torque equation also you can find electromagnetic torque developed, real part of this internal EMF into current, right? So okay, so in power unit, in fact, this equation gives us V into I conjugate. This is the power, right? Complex power, and the real part of this will give us the real power by the generator, and in fact in power unit the real power generated by the generator is in fact equal to the electromagnetic torque developed, right, in power unit. So next model is your transient or two-axis model. So in the previous case we have seen that is the subtransient model. That was the most accurate model where we are only neglecting the transmission, the network transients and the starter transients, right? But here in case of transient or two-axis model, what we are assuming that it is the further simplification of the subtransient model of the generator, and here the subtransient time constants corresponding to the damper winding 1D, 2Q are very small as compared to the transient time constant. So therefore the subtransient time constants are taken as 0. So TDO double dash and TQO double dash is considered 0. So now substituting these values, what will happen? And also your XD dash will become XD double dash, XQ dash will become equal to XQ double dash. Okay, in the transient model, because we are assuming that the effect of damper winding 1D and 2Q are very, very small. We are neglecting that. Okay. So hence your subtransient time constant can be set to 0 in all the equations by setting all the equations in all the equations the subtransient time constant 0, we'll find these equations. So from the first equation we'll get this, we'll derive this, and from the second equation in the q axis we'll get this, right? Then from the starter algebraic equation just we'll get this, then this is another starter algebraic equation, and just little bit by manipulation by substituting xt double dash is equal to xt dash, what you will get, this will become 0, right? And this part will remain, and just little manipulation will give us xt dash into id plus eq dash. Okay, and your psi d and psi q will be coming from these two equations as this. Okay, then we know psi q is minus bd minus rs id, and psi d is this. So just substitute these values here, psi d and psi q, just substitute in these two equations. By substituting, what we'll get? So okay, these equations will be there. These are the transient equations in the q axis and d axis, right? This will be there. This is further simplified because xd dash is equal to xd double dash and xq dash is xq double dash. So now substituting psi d and psi q in these two equations, we'll get the internal EMF and the terminal voltage equation. So your terminal voltage, okay, by substituting this, we'll get this equation, and then just by multiplying the second equation, this equation with J1 and adding these two equations, what we'll get? Just multiply the second equation with J1 and adding this to the first equation, we'll get Vd plus JVq plus Rs plus Jxd dash, right? Into id plus jiq, that is equal to xq dash minus xd dash iq plus ed dash plus jeq dash. Okay. Now, if we'll express this equation in the Ri axis, right? In the Ri axis, that is common reference frame, and with some additional assumption, that additional assumption is xd dash is equal to xq dash. This is true when the saliency effect is neglected, right? Saliency effect is neglected. Here also it is assumed that the saliency effect is neglected. So now assuming this, we'll find ed dash plus jeq dash, and to the common reference frame, if we are converting, obviously the factor of e to the power j delta minus pi by 2 will be multiplied across the equation, right? Across this equation. And then we'll find the equation in the common reference frame in the Ri axis, right? So this is the equivalent circuit representation in the Ri axis, right? So this is the terminal where the terminal voltage is Vd plus jVq, e to the power j delta minus pi by 2, and your internal EMF is this Ed dash plus jeq dash, where we assumed we have neglected the saliency effect, considering xd dash equal to xq dash. Okay, so this is your transient model, or we say it two-axis model. Okay, we are considering two axes, d and q, both axes. Only we are considering the transient model, right? We're neglecting the subtransient effect of the damper winding, like the effect of the damper winding 2q and 1d, right? We have three damper windings. We have considered in the model three damper windings. One is in the d axis along with the failed winding, and other two damper windings are on the q axis, right? So we're neglecting here the effect of damper 2q and 1d, but the damper 1q is there in this model. So the model representation in this is like this, right? So therefore this is known as transient model or two-axis model. It has two axes, but it represents a transient phenomenon, transient model, right? And similarly, the equation for electromagnetic torque we can derive, right? So this will be Ed dash Id plus Eq dash Iq, right? So in the previous slide, we have derived that for subtransient model, Ed double dash into Id plus Eq double dash into Iq. Just in case of transient model, just considering the transient internal voltages, Ed dash into Id plus Eq dash Iq, right? Okay. So now this is a little simpler model than the subtransient model. Now if we'll further simplify this model, that is called the Flux decay model. Okay, Flux decay model or one axis model. Okay, so the transient model can be further simplified by neglecting the damper windings 1q. We'll neglect the damper winding again in the q axis 1q, right? So that means there is no damper in the q axis now, and also we are neglecting the damper winding in the d axis, right? That is already it was neglected. Only we are now considering the field winding, right? Okay, so only the dynamics of the field winding is considered here. Therefore, it is called one axis model, or we call it Flux decay model. This is also justified as the time constant TQO dash is less compared to the time constant TDO dash. So TQO dash now will be neglected because it is very less than TDO dash when we are neglecting the effect of the damper winding 1Q. Okay. So now TQ dash is also neglected. Only TDO dash will be there. Hence, it can be set to 0. So your TQO dash is set to 0. Okay. In all the equations, and with this assumption, the equations can be written as this. So we have considered TQO dash 0, psi 1q and psi 2q both at 0. So your equations now became this. This is your d-axis and q-axis dynamic equations, and this is also d-axis equation. Further, it is mentioned here, right? And these are your rotor dynamics equation, swing equation, right? So now if we'll okay, after substituting these values here in this equation, we found this equation, right? Okay. So this is how we got here. After substituting these in these values here, we'll get this equation, right? TDO, only this TDO dash DEQ dash by DT will remain, right? This equation will become 0. Okay, TQ dash will become 0. And so ED dash equation will also become 0. So here, therefore, from this equation, we'll find XQ is equal to XQ dash. Okay. Now, further just simplifying, we'll get psi D and psi Q equation. After simplifying psi D and psi Q equation, we'll get, these are the flux linkage equations in D and Q axis. We'll get minus XD dash ID plus EQ dash, and psi Q will become minus XQ dash IQ minus ED dash. Okay. Now again, by further simplification, if we'll do just substituting psi 1q here, ed dash, then we'll find that psi d will become minus xt dash id plus eq dash, and psi q will become minus xq iq, because xq dash is xq and psi 1q is 0, so therefore ed dash will also become 0, right? Okay, so therefore your psi q and psi d will become, already we know this, psi q and psi d in terms of terminal voltage. This is the equation. Now substituting this psi q and psi d in these two equations, we'll get further, we'll get this equation. Vd plus RSID equal to XQ IQ, and VQ plus RSIQ is equal to minus XT dash ID plus EQ dash. Now if we'll multiply J1 in the second equation, in this equation, and add this both equation, these two equations, we'll get, multiplying the second equation is J1 and adding it to the first equation, it will give me this equation, right? And expressing it in the Ri axis also in common reference frame, we'll get this equation. This is the final equation which represents the generator equivalent circuit, right? So we'll get xq minus xt dash into iq plus jeq dash into e to the power j of delta minus pi by 2, that is equal to the terminal voltage in dq axis parameters multiplied with the conversion factor plus the parameters plus the current dq axis current, e to the power j of delta minus pi by 2, which is the conversion factor, right? Now if we'll represent this in the equivalent circuit form, okay, so that we can see here in this equation, this is your internal EMF, right? EQ, and I can write EQ dash, this is a transient model, right? So xt dash plus rs plus xt dash jxt dash multiplied with the current will give me the internal EMF, right? This is the equation, right? Okay. So now, sorry, this whole equation is your internal EMF, right? Okay. This has two parts, in fact. One is your real part, other one is your imaginary part, and it is obviously multiplied with the conversion factor. Okay, this is the most simplest model. Already you know this model. This is already you have studied also. This is the classical model, and we called it constant flux linkage model. That means there is no change in the flux linkage. So in the previous model we considered only field, but we consider there is a change in flux, right? But here in this model we are not considering the change in flux linkage. We are considering a constant flux linkage model. Also we have neglected all the subtangent and transients, and finally we are considering it is constant flux. Therefore we are telling this as constant flux linkage model, and it is the classical model, right? Okay, and this is the simplest model, but it is not very accurate, but it gives the information about the stability of the system. So this model is very useful in case of very large power system. If we are interested to just to know about the stability of the system, like you can use the equal area criterion on the classical model. You can know whether the stable system is stable or not, right? Very quickly we can know, or very quickly we can find the small signal stability assessment. We can also do the transient. We can just quickly apply some integration method, the numerical integration technique, to find out the time domain response. And this is very easy, right? In case of dynamic studies with a time period less than that of TDO dash are considered, then the field winding dynamics also can be neglected. If we are considering a time period in the dynamic analysis, in the dynamic studies, that is, that time period is less than the TDO dash, then we can also neglect the field winding dynamics in that case, and we can use this classical model or constant flux linkage model. So in the flux decay model, if we assume that during the period of study, the voltage behind the transient reactance XT dash is constant, is not changing, and only the electromechanical equations need to be considered in this model. So the transient voltage is computed at steady state and kept constant throughout the study. The input mechanical torque Tm is assumed to be constant, and hence the turbine and the turbine governor dynamics are also eliminated. So as we are assuming constant, this Tm, that is the mechanical input torque, is constant. So therefore here also it is assumed that the turbine and the governor dynamics, turbine governor dynamics also they are eliminated. It is also not coming into picture. So everything is eliminated. Therefore the dynamic equation model can be written as only this. Only swing equation will remain as the dynamic equation in this model, this classical model. Okay, so therefore we can represent this. If we'll represent this classical model in the equivalent circuit form, we can see that this will be your steady state voltage, okay, internal steady state voltage, which is multiplied with the conversion factor, and this is your current, terminal current, this is your terminal voltage, right? And we can easily, just by multiplying the conversion factor, we find it in the common reference frame. So this is your classical or constant flux linkage model. So all these models, what are the models we have discussed here today? One is your subtransient model, that is considering or neglecting the transient of the network and the starter. That was the first and most accurate model. And then if we'll do the further simplification by neglecting the effect of the damper winding 2Q, right? Then we get the two-axis model, right? We call it two-axis model or transient model, transient or two-axis model, right? Then with further simplification, we get flux decay model or one-axis model where we further neglected the effect of the damper winding 1Q, right? And then the most simplest model is the classical or constant flux linkage model where we have neglected the effect of flux linkages, right? All the flux linkages, including the field winding. So these four models we have studied here, and most of the time in our analysis, in our applications, we use these four models only. And most accurate model is the subtransient model, right? Okay. So maybe it will be over now. Okay. So this is done. So now I'll stop here. Thank you very much.